astronomers still struggle with uncertainty in their quest to comprehend the first stars and galaxies that illuminated the universe. However, they are getting closer to enlightenment with each new discovery. The James Webb Space Telescope, JWST, a $10 billion time machine that is currently in its first year of observations, has made unprecedented discoveries that point to this undeniable fact. JWST was intended to reveal the weak infrared sparkle of the universe's earliest radiant particles. Webb's vision, which extended back to the first few 100 million years after the Big Bang and provided superior data on newborn galaxies to any previous facility, exceeded expectations. Researchers like Charlotte Mason, an astrophysicist at the University of Copenhagen, have been taken aback by the abundance of these early galaxies, which has exceeded even the most optimistic projections. Dozens of candidate galaxies have emerged, which has astonished them. Theorists and observers alike have paid close attention to these early galaxies' surprising maturity. Are these strangely large and bright galaxies real, or do they point to a universe that is very different from what we've previously thought? Do they pose a threat to the Big Bang Theory as a whole? Come along with us as we investigate how the James Webb Space Telescope has altered our perception of the universe. On the whole, we should rewind to the introduction of the universe. The cosmic dark ages began when electrons, protons, and neutrons merged into neutral hydrogen atoms as the universe warmed up following the Big Bang. Then a crucial occasion happened. The elusive dark matter that made up the majority of the universe's mass began to exert itself, resulting in the first stars being formed. During the time of reionization, these stellar beacons illuminated the universe and set off a chain of events that shaped galaxies within a vast cosmic web. In the meantime, the discoveries made by Edwin Hubble in the 1920s demonstrated that the universe is expanding. The mysterious dark energy represented by the Greek letter lambda is accelerating the universe's expansion, according to further observations, including those made by the Hubble Space Telescope. The lambda cold dark matter (CDM) model, which is consistent with a plethora of observational data, resulted from this comprehension. With the Hubble telescope, astronomers began their investigation of the earliest structures in the universe. Hubble spotted thousands of galaxies in 1995, many of which were older than expected. In 2016, Hubble found GNZ11, a system 400 million years after the enormous detonation. However, in order to determine whether GNZ11 was an anomaly or a member of a larger group of early galaxies, astronomers required a more powerful instrument. The James Webb Space Telescope is here. JWST carries a massive segmented mirror and sensitive instruments designed to investigate cosmic dawn. It is 1.5 million kilometers from Earth and has been cooled to close to absolute zero. Its underlying revelations have offered looks at cosmic systems incredibly near the universe's starting point and exoplanet environments with exceptional accuracy. The CDM model and our understanding of cosmic evolution are being challenged by these discoveries. Analysts have discussed JWST's discoveries, especially the revelation of splendid early cosmic systems a lot bigger than those displayed in lambda CDM reproductions. These inconsistencies could be resolved, according to some, if early galaxies evolved much more rapidly than galaxies do today. Other people think that the brightness of early galaxies could be caused by a variety of things like gas cooling or black holes. A critical instrument for understanding these systems is spectroscopy, which investigates the frequencies of light to decide their distances. Early JWST perceptions, depending on photometry, have now been supplemented by spectroscopy, affirming worlds as far back as 13.2 a long time back. Recreations led by specialists at the College of Memphis have shown that the lambda CDM model can oblige a portion of these early worlds. In addition, the results of JWST suggest that population 3 stars, the first stars in the universe, may have contributed to reionization. JWST's findings are significant, challenging the CDM model and reviving debates regarding cosmic evolution. However, our understanding of the universe may develop further as additional data are collected, revealing a universe that is even more amazing than we could have ever imagined. The initial findings of JWST have reverberated throughout the scientific community, raising brand new concerns regarding the veracity of established models like CDM and the nature of the universe. Even though the CDM model has been a cornerstone of modern cosmology because it matches the majority of observable data and explains the distribution of galaxies, dark matter, and dark energy, the telescope's findings may indicate that our understanding is incomplete. Particularly intriguing is the discrepancy between the predicted brightness and mass of early galaxies based on CDM simulations and those observed by JWST. The JWST-observed galaxies appear to have formed quickly, accumulating mass and stars much faster than anticipated for that early stage. Our models may underestimate the rate at which stars and galaxies can form in the chaotic early universe because of this rapid formation. In an effort to reconcile JWST's observations with the CDM framework, scientists have turned to computer simulations to test various scenarios. Some propose changes to the underlying mass capability IMF, the circulation of heavenly masses upon entering the world, recommending that early stars could have framed all the more much of the time as monstrous iridescent articles. JWST's discovery of unexpectedly bright galaxies could be explained if this is true. Another possibility is that early galaxy formation was significantly influenced by black holes, which are formed when massive stars collapse. The brightness of early galaxies may have been affected by supermassive black holes that were observed at redshifts of 6 or 7, representing the universe approximately 1 billion years after the Big Bang. Accumulation circles around these dark openings could discharge serious radiation, possibly helping the general iridescence of worlds. Additionally, the findings of JWST point to the existence of population 3 stars, an elusive generation of stars made almost entirely of hydrogen and helium and created from the pure gas that remained after the Big Bang. If these stars are true, they would help us understand how the universe was reionized, a crucial process that made it possible for light to move freely through space and created the universe we see today. The implications of these findings for cosmology remain cautiously optimistic as the telescope continues to collect data. Although it is evident that JWST is providing valuable data, it is still unknown whether this data will fundamentally alter our understanding of the universe. The Lambda CDM model has endured difficulties previously, and keeping in mind that JWST's disclosures have uncovered areas of vulnerability, they may likewise move refinements to existing hypotheses as opposed to their altogether excusal. According to Michigan State University researcher Megan Donahue, comprehending the universe's earliest stars and galaxies is comparable to putting together a puzzle with missing pieces. Every disclosure makes new sections visible, yet the full picture stays tricky. In the meantime, Rachel Somerville of the Flatiron Establishment stresses that while we are seeing earth-shattering science, it's fundamental to stay purposeful, utilizing JWST's uncommon goal and aversion to thoroughly test our expectations. Additionally, the significance of collaboration in astronomy is emphasized by JWST's findings. Astrophysicists, cosmologists, and particle physicists from various fields are working together to interpret the telescope's discoveries because its data have attracted global interest. From dark matter and energy to the nature of stars and galaxies, they are working together to push the boundaries of what is known about the universe. Looking ahead, even more exciting revelations are anticipated in the years to come. By capturing light from even earlier epochs and further enhancing our understanding of the cosmic dawn, JWST will continue to peer deeper into the universe. Scientists will be able to test and improve cosmological models with the assistance of spectroscopic measurements, which will help clear up any lingering doubts about the distances and masses of the galaxies that JWST has observed. All in all, the James Webb Space Telescope is changing the account of astronomical development, stretching the boundaries of human information. The universe's origins, the birth of stars and galaxies, and the fundamental laws that govern them all are challenged by its observations, which also open up new avenues for understanding. Whether it supports or changes our ongoing models, one thing is sure: JWST is introducing another time of revelation, one that vows to develop our enthusiasm for the universe and our place inside it.